Imagine waking up, you are jolted out of a deep sleep by that unmistakable, piercing screech of an emergency push alert on your phone.
Oh, that just instantly spikes your heart rate.
Right. You grab it, squinting at the glaring screen in the dark, and your stomach just drops. A massive hurricane that meteorologists confidently stated would harmlessly skirt the coast has just violently shifted course.
And it is now heading straight for your town.
Exactly. The evacuation window is closing fast. But I want you to look past the panic for a second, because the origin of that life-saving alert represents a fundamental shift in human history.
A massive shift.
That updated forecast didn't come from some warehouse-sized, supercomputer-crunching complex fluid dynamics equations over the last 6 hours. That alert arrived just minutes after a satellite passed overhead.
Right. Generated by a machine-learned model that analyzed decades of atmospheric patterns in a matter of seconds.
Which is just wild to think about.
It really is. And I mean, this is a scenario playing out in emergency management centers right now. We are witnessing this profound tension between the breathtaking speed of new silicon technology and the absolute non-negotiable necessity of human trust.
Oh, because the stakes are so incredibly high.
Yeah, when you are asking 1 million people to abandon their homes based on a forecast generated in 3 minutes, the architecture of how we predict the future has to be flawless.
Welcome, listeners, to another My Mind MashUps Deep Dive, where we unravel mysteries, spark curiosity, and make sense of complex ideas together.
And we are so glad you're here with us.
Every single deep dive we do is built on 3 core pillars: sparking curiosity, challenging assumptions, and expanding understanding. Also, before we get into the mechanics of all this, we want to take a quick moment to warmly thank all the listeners who show their appreciation recently by buying us a coffee.
Yes, thank you so much. It honestly keeps the research engines running, and we genuinely appreciate it.
We really do. And to everyone tuning in, don't forget to like, share, and subscribe if you enjoy content that makes you think. So, to set the stage for you, what exactly are we unpacking today?
Well, we are going to explore how AI is fundamentally disrupting traditional weather forecasting. We will break down the mechanics of this huge shift from physics-based supercomputers to lightning-fast AI models.
The silicon meteorologists, basically.
Exactly. We'll examine the specific algorithms driving this change, how global weather agencies are adapting to all this commercial tech, and ultimately what this means for public safety when a machine makes a mistake.
Because machines definitely still make mistakes.
Oh, absolutely.
So the computational wall that traditional forecasting hit is really what left this massive opening for Silicon Valley to step in. But to grasp the magnitude of this shift, we really need to understand the structural bottleneck of the old way of seeing the sky.
Right, the baseline.
Yeah, let's talk about numerical weather prediction, or NWP.
So NWP is an incredible feat of human engineering, but it is heavily constrained by physics and math. It starts with this process called data assimilation.
Which sounds intense.
It is. Meteorologists have to collect millions of fragmented, non-uniform observations from across the globe. You've got temperature readings from commercial aircraft, pressure data from floating ocean buoys, infrared scans from satellites.
It's a chaotic mess of data points.
Exactly. And harmonizing all that chaotic data into a coherent 3D mathematical grid that represents the current state of the entire global atmosphere is a massive inverse problem.
So it takes immense computing power just to figure out what the weather is doing right now, let alone in the future.
Yes, that is literally just step one. Once I have that initial state, the traditional model then steps forward in time. It explicitly calculates the Navier-Stokes equations for fluid motion.
The heavy physics stuff.
Right. Fluid motion, thermodynamics, moisture processes, all calculated for every single point on that massive 3D grid. Take NOAA's high-resolution rapid refresh model, the HRRR.
I've heard of that one.
Yeah, it enforces the fundamental laws of physics, things like the conservation of mass, energy, and momentum. Because it is strictly bound by these laws, it is highly accurate.
But there's a catch.
A huge one. Computing the physics for every grid point, step by step into the future, requires thousands of processors. It takes a massive supercomputer hours to produce a single forecast run.
Okay, so traditional forecasting is like Baking a cake by mathematically calculating the chemical reactions of every single grain of sugar and molecule of flour.
That is a perfect way to put it.
Like, it's incredibly accurate to the laws of physics, but doing the math takes absolutely forever.
Right. And machine-learned models sidestep the chemistry entirely, sticking with your analogy. They don't explicitly solve any equations of motion.
Wait, none at all?
None. Instead, they use neural networks to map atmospheric straits. So they ingest what the weather looked like 6 hours ago, look at the weather right now, and learn the statistical relationships to output the weather 6 hours from now.
Ah, so they just connect the dots based on history.
Precisely. The heavy computational lifting is done during the training phase, which, might take weeks. But once the model is trained, the inference, the actual forecasting part, happens in seconds.
That speed difference is staggering.
It's game-changing. For example, NOAA's experimental AI version of their high-resolution model, HRRCast, runs at a 3-kilometer resolution and produces a full forecast in about 7 minutes on a single computer chip. Just one GPU.
That is mind-blowing. But I have to pause on the mechanism there.
Go for it.
If the AI is just mapping state A to state B, probabilistically, it doesn't actually know the laws of physics, right?
Correct. It has no inherent concept of physics.
So it's basically learning the symptoms of the weather rather than the underlying disease. Does that mean it could accidentally predict something physically impossible, like water flowing uphill or a hurricane generating energy out of nowhere, simply because it hallucinated a statistical pattern?
The short answer is yes. And honestly, it is the central vulnerability of this entire technology. Because AI models do not inherently conserve mass or momentum, their outputs are not physically constrained.
You're just guessing based on what they've seen.
Right. They only know the multidimensional landscape of their training data. If the atmosphere enters a new physical regime, or there's a rare extreme event that wasn't heavily represented in the historical data, the statistical mapping just breaks down.
And it just makes something up.
Exactly. The model can confidently output an atmospheric state that literally defies the laws of thermodynamics.
Wow. The AI faking it until it makes it, but doing it with such statistical precision that it rivals a billion-dollar government supercomputer. That is fascinating.
It really is the ultimate double-edged sword.
And that speed advantage brings us to the actual algorithms dominating the space. We're seeing software companies outmaneuvering traditional meteorological institutions, aren't we?
Oh, the speed of disruption is completely unprecedented. Let's look at Google DeepMind. They released GraphCast, which uses a graph neural network.
Which is different from the 3D grid you mentioned earlier.
Very different. Instead of a rigid 3D grid, a graph maps nodes and edges, allowing the model to route information globally much faster. They trained it on 4 decades of historical weather data, specifically the ERA5 dataset.
What's the ERA5 dataset?
It's a meticulously reconstructed physical record of the global atmosphere, basically the gold standard of historical weather data. And with that training, GraphCast can predict 10 days of global weather in under a minute on a single TPU chip.
Under a minute for 10 days of global weather, that's absurd.
It gets crazier. In testing, it outperformed the European Standard Model, the ECMWF, which is widely considered the absolute gold standard of traditional forecasting. GraphCast beat it on over 90% of test targets.
A 90% outperformance against the ECMWF isn't just an incremental update, that is a structural upending of the whole hierarchy.
Absolutely, and they moved past deterministic forecasting pretty quickly after that.
Deterministic meaning just giving one single prediction.
Right. They realized they needed probabilistic models. So DeepMind introduced GenCast in late 2024. GenCast is a diffusion-based model, similar to the architecture used in AI image generation, but applied to the atmosphere.
Oh, that's wild, like Mid-Journey for clouds.
Sort of, yeah. It generates a 50-member ensemble for 15-day forecasts. Ensembles are vital because running many slightly varied probabilistic outcomes gives forecasters a spread of uncertainty.
So they can see the range of what might happen.
Exactly. And GenCast beat the European ensemble on 97% of evaluation targets, showing incredible skill at mapping out extreme heat, winds, and cyclones.
If this is resonating, hit that subscribe button so you don't miss the next deep dive. So Google is dominating, but they aren't the only ones in the game, right?
Not at all. Microsoft has also moved into this space with Aurora, and their approach highlights a completely different architecture.
How so?
Aurora is a 1.3 billion parameter foundation model. By leveraging massive parameter scaling and a 2-phase training process, it learns the latent representations of atmospheric dynamics generally, and then fine-tunes for specific tasks.
Okay, so it builds a broad understanding first, then zooms in.
Exactly. And the versatility of a foundation model changes the economics of forecasting entirely. Aurora doesn't just predict temperature and precipitation. It forecasts air quality, ocean wave heights, and tropical cyclones simultaneously. All at once. It outperformed traditional models in 100% of tropical cyclone benchmarks. And for smaller national meteorological services around the world that cannot afford to build or rent massive supercomputers, OpenWeight's foundation models suddenly provide access to top-tier localized forecasting.
It levels the playing field globally.
It really does.
Then you look at Google's release of WeatherNext 2 in November 2025. They used functional generative networks to produce hundreds of high-resolution scenarios in under a minute, down to local 1-hour resolutions.
The granularity on that is just incredible.
Yeah, but what stands out to me isn't just the math, but the distribution model. Google made WeatherNext 2 available on Google, Earth Engine, and BigQuery.
Right, making it accessible to businesses.
Exactly. High-level weather prediction is moving from sovereign government supercomputers to B2B enterprise software. Logistics companies rerouting supply chains, airlines optimizing flight paths, or agricultural firms planning harvests, they can now run their own custom high-res AI weather models on demand.
It democratizes access, for sure, but it also fragments authority.
That's a good point.
When enterprise software can predict a storm faster than the National Weather Service, it creates a very complex dynamic for emergency management. The real metric of success isn't outperforming a benchmark in a tech demo, right?
Right, it's about real-world application.
Exactly. It is operational adoption by the agencies whose primary mandate is public safety.
Because you really don't want a city mayor betting an evacuation plan on a tech company's API.
No, you absolutely do not.
So, how are the major government agencies integrating this without compromising their safety mandates?
Well, the European Center for Medium-Range Weather Forecasts, the ECMWF, they moved aggressively. In February 2025, they made AI operational by launching the Artificial Intelligence Forecasting System, or AIFS.
And are they just replacing their old system?
No, they run it concurrently with their traditional physical model. The AI uses 1,000 times less energy, and for tracking the path of tropical cyclones, it actually performs up to 20% better.
That energy saving alone is massive.
It is, and they didn't stop there. By July 2025, they deployed an ensemble version with 51 members that runs 10 times faster than the physics-based equivalent.
What about the US? What is NOAA doing?
NOAA's response was equally rapid. By December 2025, they deployed the AI Global Forecast System, generating a 16-day global forecast in 40 minutes using just 0.3% of the computing power of their traditional model.
0.3%, that's almost nothing.
Barely a rounding error in energy costs. But the architecture that really bridges the gap for them is their hybrid GEFS. They combined 31 physical ensemble members computed on the supercomputer with 31 AI ensemble members.
Oh, combining the old and the new.
Yes, and they found that this 62-member hybrid consistently outperforms both the AI-only and the physics-only systems.
That makes total sense. The hybrid approach structurally hedges the weaknesses of both paradigms.
Exactly. NOAA actually based their AI on Google's GraphCast architecture, but they fine-tuned it using their own proprietary data assimilation techniques. That allowed them to harmonize it perfectly with their physical models.
We also have to look at severe, localized convective weather, right? Like predicting a tornado requires mapping variables like wind shear and helicity, highly complex vorticity dynamics that statistical models historically struggled with.
Oh, big time. Tornadoes are incredibly hard for AI to grasp.
But NOAA's version 3 upgrade to HRRcast in March 2026 pushed the resolution to 3 kilometers. They trained it on 9 years of high-resolution radar and satellite data and integrated those exact variables. It processes the convective environment 100 times faster than the traditional HRRR.
And the tactical advantage of that processing speed becomes completely obvious during rapid intensification events.
Like, comment, and subscribe to hear more My Mind MashUps deep dives. Because during the 2025 hurricane season, the U.S. National Hurricane Center leveraged that exact speed advantage.
They did, and it was a crucial test.
Forecasters use the experimental AI models as a rapid sounding board. Because the AI forecasts arrived in seconds, meteorologists could instantly explore multiple track and intensity scenarios.
Right, it wasn't replacing the human analysis at all.
Exactly. It provided a high-speed second opinion, allowing them to refine the warning cone while the traditional physical models were still churning through the math.
Wallace Hogsett, the science operations officer at the NHC, he framed it perfectly. He said AI models provide an additional lens on the future atmosphere. But the human forecasters immediately recognized the systemic limitations.
Like what?
Well, the AI really struggled with temporal resolution during rapid extreme intensity changes. It couldn't quite capture how fast a storm was blowing up.
Which brings up the most critical friction point in this whole transition.
Yeah.
If these AI models are thousands of times faster, run at a fraction of the energy, and track cyclones 20% more accurately, the obvious fiscal question for a government agency is, why keep paying the massive electric bills for the supercomputers? Why not just unplug the traditional physics models entirely?
I mean, on a spreadsheet, it looks tempting, but unplugging the physical models would be a catastrophic single point of failure because of how the machine stumbles.
Right, the physics hallucinations we talked about.
Exactly. The 2026 Rice University study explicitly highlighted the danger of abandoning physical realism. They analyzed models like Pangu weather and Aurora during cyclonic events. The AI predicted the cyclone's track with stunning accuracy.
But the internal dynamics were wrong.
Completely distorted. It completely messed up the wind field structure and intensity. It failed to conserve angular momentum.
So, meaning the algorithm correctly maps the pixels, showing where the storm will make landfall, but fundamentally misunderstands the physics of the storm itself. It wildly underestimates the destructive force of the winds when it actually hits the coast.
That is exactly the danger. You have a model confidently outputting an outcome that is structurally impossible.
That's terrifying.
And there was a separate study published in April 2026 analyzing low-level boundary layer wind jets that proved this complementary error.
What did that study find?
Well, the physical ECMWF model systematically overestimated the jet intensity due to how it parameterized friction, but the AI model systematically underestimated the intensity because statistical algorithms tend to smooth out extremes to minimize mean squared error during training.
Right. So the AI is like a brilliant student who memorized the answers to every past exam to get an A+2, but never bothered to learn the underlying subject.
Spot on.
When the atmosphere throws a completely novel out-of-distribution event at the model like a trick question it hasn't seen in its historical training data, it doesn't just fail. It fails with total spectacular confidence.
It does. And that leads to the ultimate liability here, the black box problem. An AI model operates on billions of parameters mapping latent space. When a physics-based model produces a bizarre forecast, atmospheric scientists can actually open the code, trace the fluid dynamics equations, and diagnose exactly where the parameterization failed.
You can follow the math.
Right. But when an AI model hallucinates a Category 5 hurricane out of nowhere, humans cannot untangle the complex, multidimensional statistical weights to understand why it did that.
And if an emergency manager has to legally justify a billion-dollar evacuation order, they cannot rely on a black box. They need transparency.
100%.
The origin of the forecast has to be defensible. A blazing fast 10-day prediction is practically useless if the people responsible for public safety don't trust the mechanism generating it.
Trust really is the bottleneck of operational integration. The National Science Foundation funded the AI2ES program specifically to study risk communication in AI environmental forecasting.
What did they find out?
Their research revealed two opposing psychological dangers. The first is algorithmic aversion. Forecasters reject the AI guidance because they can't interrogate its logic. If the uncertainty isn't clearly represented, they just default back to the physical models they understand.
Which means ignoring a potentially life-saving tool.
Yeah.
But what's the other danger?
The inverse of that is automation bias, which is arguably much more dangerous.
Yeah, I can see that.
A decision maker looks at a crisp, high-resolution AI forecast on a beautiful display, assumes the computer possesses superior analytical capability, and overrides their own local meteorological intuition and ground observations. They blindly trust the machine.
Wow. Which is why the global meteorological community drew a hard line, didn't they?
They had to. The World Meteorological Organization issued a defining standard in 2025. They established that AI must be integrated to complement, not replace, human forecasters.
Right. The human in the loop.
Always. Humans must remain the authoritative voice to ensure universal warning coverage and accountability by 2027. We simply cannot delegate the final life or death call of public safety to an opaque algorithm optimizing for mean squared error.
The new atmospheric lookout isn't a zero-sum game of man versus machine. It is a necessary collaborative hybrid. We require the breathtaking computational speed of neural networks to process a chaotic climate, but that speed must be anchored by the physical constraints of traditional models and the accountability of human judgment.
Well said. The machine reveals probabilistic patterns hidden within decades of atmospheric data, freeing forecasters from the burden of raw calculations so they can actually focus on communicating risk.
And the meteorologist's deep understanding of local topography and physical reality keeps the entire system from hallucinating. I want to leave you with a final provocative thought to mull over. As AI models become the dominant forecasting tool, they will generate massive volumes of synthetic weather data. If future models in the 2030s are trained on datasets that increasingly include the outputs of previous AI models, do we risk creating an atmospheric echo chamber?
Oh, that's a fascinating problem.
Right? Will the algorithms begin learning from their own past hallucinations, slowly drifting away from the reality of the physical sky?
It's the classic paradox of automation. The more we rely on a machine to translate the world for us, the harder we have to work to verify it is still looking at the real world.
Drop your thoughts in the comments. Your perspective could shape our next deep dive. Think about that next time you get a push alert about a storm on the horizon. Was it the immutable laws of physics, or was it a statistical pattern that saw it coming? Find My Mind mashups everywhere you listen. Amazon Music, Audible, Facebook, Pocket Casts, Spotify, TikTok, and YouTube.
Thanks for listening, everyone.
Until next time, keep questioning what you see.